Chemistry of Baking Sugar Cookies by Arunima, Ashwittha, and Samantha. The physical changes of the sugar cookies are that the surface hardens and the cookies change shape and size. The chemical changes include the color of the cookies darken and the properties of the baking soda causes the cookies to rise. The safety considerations include washing your hands before baking, wearing an apron, and using an oven mitt when removing the cookies from the oven.
For this recipe, you will need 2 3/4 cups all-purpose flour, 1 teaspoon baking soda, half teaspoon salt, 1 1/4 cups margarine, 2 cups white sugar, 2 eggs, and 2 teaspoons of vanilla extract. First, you need to preheat the oven to 350 degrees. In a medium bowl, stir together the flour, baking soda, and salt. Set aside. Next, in a large bowl, cream together the margarine and 2 cups sugar until light and fluffy. Beat in the eggs one at a time, then the vanilla. Gradually stir in the dry ingredients until just blended. Roll the dough into walnut-sized balls and roll the balls in the remaining 1/4 cup of sugar. Place the cookies 2 inches apart onto ungreased cookie sheets and flatten slightly. Bake the cookies for 8 to 10 minutes in the preheated oven until lightly brown at the edges. Allow the cookies to cool on the baking sheet for 5 minutes before removing to a wire rack to cool completely. We chose to serve the sugar cookies for breakfast. One batch makes 40 cookies and we need to make 35,000 cookies. We used factor label to determine the number of batches. We multiplied the 35,000 cookies and the one batch. We divided it by 40 cookies and we got 875 batches. By using the factor label method, we were able to determine the amount of each ingredient we need to make 875 batches of cookies. We multiplied 875 by a fraction of 1 teaspoon of baking soda over one batch. This showed us that we need 875 teaspoons of baking soda to make 875 batches of cookies. This is a reaction for the decomposition of sodium bicarbonate, also known as baking soda. The decomposition of baking soda breaks down 2 moles of solid sodium bicarbonate to form 1 mole of carbon dioxide gas, 1 mole of dihydrogen monoxide gas, and 1 mole of solid sodium carbonate. This reaction is an example of an endothermic reaction. This model shows what happens to the molecules during the decomposition of baking soda. Compounds form single or double bonds because compounds are more stable if the elements in the compound have noble gas electron configurations. The law of conservation of mass states that matter cannot be created or destroyed. Because of this, we had to balance the reaction by adding a coefficient of 2 in front of the sodium bicarbonate compound. This ensured that we had the same number of each element on the reactants and the product side. Decomposition of baking soda is important to the quality of the cookies. When baking soda decomposes, carbon dioxide is produced, which forms bubbles in the cookies. This helps make the cookies lighter and less dense. The decomposition of baking soda is an endothermic reaction because energy is required as the reaction progresses. The change in energy value is positive. This is because more energy is absorbed when bonds break. Below is a diagram representing the change in potential energy as time goes by during the decomposition of baking soda. Since the decomposition of baking soda is an endothermic reaction, the reactants absorb energy to break bonds. Bonds then form in the product as a partial amount of absorbed energy is released. The graph shows us that more energy is absorbed than released, causing this reaction to be endothermic. This is the chemical reaction for the decomposition of baking soda, and underneath are the bond energies of the reactants and the energy of the products. To calculate the enthalpy change, we have to first find the bond energies of each molecule. 2 moles of sodium bicarbonate has the bond energy of 4,050 joules per 2 moles. Carbon dioxide has the double bond, so we have to multiply 745 joules per mole by 2, which gives us 1,490 joules per mole. Water has 2 OH bonds, so we multiplied 464 by 2, which gave us 928. Sodium bicarbonate has a bond energy of 1,501. These bond energies tells us how much energy we need to break down a compound. Thermochemical equation includes the balanced chemical equation, also the enthalpy change. Since energy is needed to release, the sum of the bond energies of carbon dioxide, water, and sodium carbonate has to be negative, which gives us negative 3,919 joules per mole. Since our reaction is endothermic, the change in energy value is positive. To find the enthalpy change, we add the sum of the bond energies of carbon dioxide, water, and sodium carbonate to the bond energies of 2 moles of sodium bicarbonate. We end up with a calculation of 4,050 joules per mole plus negative 3,919 joules per mole, which gives us an enthalpy change of plus 131. Since the reaction is endothermic, the plus 131 joules per mole is placed in the reactants. This leaves us with our final thermochemical equation.